holiday sa December 8 or na-move ba yung holiday? Hindi ko alam kung nakasama siya sa proclamation ng holiday economics. Do you guys know? Ayan, nasama pa sa recording yung backstage usapan natin. Paplano na kasi ako for next week. Hindi nyo rin sure. All right. So, good morning again, everybody. We're now recording and welcome to, I guess, week 13 of the semester. So, konti na lang, nasa finish line na tayo. So, I'll try to finish the coverage of the course. Probably siguro tapusin na natin ngayon kung kakayanin. And then on Thursday, we can talk about the other requirements that you are left with. Meron pa tayong isang homework at saka isang problem set at saka yung project. So beginning next week, probably you can work on your projects, all right, and then at the same time also work on the problem set. I'm thinking the next homework or the last homework will be due. Probably I'll give you until December 9 para dun sa sulat ko na. So ito yung tentative plan natin. Pero most likely ito na rin yun, tentative plan. So we have a homework. Do you remember what number? Anong number na tayo sa homeworks? Halatang hindi pa nag-check ng latest homework. Tingnan ko yung last.
7, sir.
Sorry, homework 6. So we have homework 7. Final homework, pero i-double ko yung count nito. So, I mean, this will be worth 10 points. And okay lang ba kung i-due natin siya December 9? Or may sinabi ba akong date? Hindi ko kasi napanood yung recording last time kasi I was looking at YouTube. Hindi ko pala siya na-upload ng maayos. So, in-upload ko lang siya uli kanina. Hindi ko na siya napanood after ko siyang i-upload. Pero is it okay if we do it December 9? Or do you want to do it say after ng December 9 and possible na December 12? December 5 ang sabi ko. Pero I'm willing to extend it to December 9. December 9. Okay. Feeling ko naman mas okay sa inyo yung mas pinapalayo kaysa mas pinapaaga, no? So if you already scheduled it for December 5, then that's fine. So pasan nyo na siya ng December 5. And if you have hectic schedule with that, pwede nyo siyang ipasa on the deadline, December 9. Then we have problem set 2, the second problem set. And this would be due on the last day of classes. Last day of classes is December 21. Tama ba? Okay, December 21. But of course, you can submit it earlier if you want. I'll probably give it to you December. It's a November. Okay. Nasa na ako. Mali-mali yung calendar ko dito. So December 21, last day of classes. So I will give it to you on December 9. I'll give problems of set number 2 on December 9. Release. Then the problem set is due December 21. Well, I can extend it. Papasko ko na sa inyo, no? Extendable until December 24, right before Noche Buena, ano? So, pero if you don't want your your Christmas break to be ruined, then plan to submit it by December 21st. And then the final project, I'll divide it into 2 parts. So first we'll have a project pitch, or basically it's a proposal, parang proposal presentation, but not a formal presentation. So we can actually do it as an elevator pitch, maybe 1 to 3 minute talk about what you plan to do. Hindi kailangan na meron pang parts na review of related literature. Hindi na kailangan na merong introduction. So hindi, maganda may introduction para masabi niyo yung motivation, but hindi niyo na kailangang i-discuss kung ano yung related literature. So basically, you'll just tell me ano yung gusto niyo gawin and how do you plan to do it. But essentially, meron lang naman tayong several options, no? So ang methodology natin, meron kayong isang problem from your field of application, so probably you can talk about it a little bit and the motivation behind that project. Then specify what's the problem that you want to solve, what's the inverse problem behind it, and then next is how do you plan to solve it. So you can talk about what's your plan for the discretization. Halimbawa, meron kang wave equation na gustong hanapan ng inverse problem, or meron kang inverse problem involving the wave equation that you want to tackle. Then you'll just tell me, sir, kasi nabasa ko, ito po yung nagmo-model ng halimbawa heat advection, ano, or how heat flow through an advection process in the media. Ito po yung nakita kong equation na medyo interesting po yung application niya, tapos kamukha po siya nung ginawa nating heat equation sa klase. So, hindi siya wave equation, heat equation to. So, tapos pwede nyo sabihin, my plan is to try to discretize the continuous problem, like what we did with the heat equation, and then find the solution by using regularization techniques. So, kailangan nyo pang tingnan kasi kung anong regularization technique yung gagana. Baka kasi yung L-curve hindi gagana o yung Morozov ay hindi gagana. So probably you can try truncated SVD. And you can go beyond the content of the course. Probably you can search the literature kung gusto niyo talaga makahanap ng magandang reconstruction. Ano? Kasi minsan nag-fail yung L-curve. Ano? So hindi siya ganon kagandahan. So posible na maghanap ka ng ibang methods. But that's fine. But you don't need to do it if you don't have really time to, kasi baby research project lang naman to. So you can just stop. Try L-curve, try Morozov. Pag hindi sila gumana, try truncated singular value decomposition. At pag hindi gumana yung tatlong methods na diniscuss natin sa klase, then you'll just mention, sir, hindi nag-work. Lalagay ko na lang sa recommendation na i-try ibang regularization processes. So probably we can schedule the project pitch. Kailan nyo gusto? December 21? Siguro a little earlier, like December 15 or 17. Para may time pa kayo to edit it. And then the following week, the week of, hindi na naman yung calendar continuity. So, ang tamang dates ay 13 and 15. 13 or 15. Tapos, para may konti pa tayong time, kung mayroon ako sa inyong isa-suggest, then you still have time until the last day of classes on the 21st to work with your group mates to finalize your project. And then, at least before the Christmas break, meron na kayong plano. Meron kayong idea. If you get bored during the Christmas break or you want to avoid some of your relatives, gusto nyo magpaka-introvert during the Christmas break, then work on the project, but it's not required. Anyway, the deadline for the project will be the last day of the final exam, the final week. So tingnan natin sa registrar. Hindi ko alam kung may nilabas ng schedule ng registrar, but I'll keep you updated. I can allow you to submit it at the last day of finals. So siguro ang pinaka maagang posibleng last day of finals ay January 6. So deadline January 6. Kung sabi ng registrar January 11 yung last day of finals, then January 11 yung deadline ng final project. Okay? So I'll keep you updated with that so that you'll have at least 1 week after the Christmas break. So ang tapos ng Christmas break ay January 2 or 3 yata. So you can work and you can go back in acad mode. So that will be the final presentation here for the final output. Oh, thank you, Prince. January 4 to 11 daw yung final exam. So the final output will be on January 11. So yan yung gagawin natin deadline. So you still have probably 8 days at least on January to do your project. Ilan yung gusto nyong members ng group? Hopefully nagsimula na kayong mag-usap-usap, ano? So siguro at most 3 members per group, but most 3 per group. And then I'll mention the formats, the possible formats for the final report. Yung project pitch would be an elevator pitch talk about 1 to 3 minutes. So you can decide sino yung magrepresent, lahat ba kayo yung magrepresent. Maiksi lang, and make it informal, just for me to have an idea of what you plan to do at para mag-gauge ko rin kung feasible siyang magawa in 1 week's time. Okay? Then the final output, I'll think about it if I will require you to write a manuscript, a research article type report, or oral presentation. So pag-isipan ko yung final output. Okay? I'll tell you the details next meeting or next week. Okay. So and I guess that's it. So this is our calendar for the rest of the semester. Any appeals? Okay lang ba yan? So ay kalendaryo na yan. Kasi alam ko marami na kayong gagawin starting next week kasi patapos na yung sem. So I hope Math 191 will not be too much of a burden. Okay. So pagaanin natin ng konti. Okay. So with that out of the way, so siguro kung wala kayong comments or reklamo doon, let's talk about the truncated singular value decomposition. So the truncated singular value decomposition, or TSVD for short, is a regularization technique that takes advantage of the singular value decomposition of a matrix. So hopefully you have watched this in the video, and it was really a nice video. I hope you appreciated it. Mamaya pa ako manonood or magbabasa ng inyong mga reaction videos or podcasts or reaction papers. Ano? Pero I hope you got the intuition behind singular value decomposition. Don't worry kung hindi nyo nasabayan yung mga technical terms like the matrix rank, the linear combination thing, orthonormal basis, that's fine. And the computations itself of the singular value decomposition, because it's not this class is not a linear algebra class. Ano? So isang tool lamang para sa atin yung singular value decomposition. And luckily, MATLAB has an intrinsic way of computing the full singular value decomposition of a matrix. So hindi natin problemahin paano mag-compute ng SVD. So i-reserve nyo na lang yun sa Math 120 or sa AMAT 105 nyo, yung pagko-compute ng singular value decomposition. But all we need to do is, what we need to talk about is to see how is it significant in finding a regularized solution for a rectangular system, and usually a system that is born out of an inverse problem. So if you will recall, we can consider a m by n matrix. Tapos yung m by n matrix na yan, hindi necessarily real yung laman niya. So it could be it might be comprised of complex numbers. Pero pwede rin namang real lang. Pero i-generalize ko na yung statements ko. Mag-apply din to kung ang entries natin ay mga complex numbers. So we have a rectangular matrix m by n. There's no restriction actually on m and n, but we will later assume that m is much greater than n. Kasi nga, yung number sa atin, sa ating mga problems, yung number of rows corresponds to how many measurements we are taking, right? Because every row will correspond to a measurement. Kasi meron kang ax equals b, so yung b natin is a column vector. Each of the entries in that column vector b are data measurements or data points. So bawat row corresponds to a data point. So yung matrix A natin, pwede natin i-assume to be a very tall and usually thin matrix. So matangkad siya na mapayat kasi gusto natin maraming data na magagamit, so M is large, pero konti lang yung unknown N, which is the number of columns. Now, and we have, sabi ko na kanina, we have a vector of data measurements. So this is C to the m, right? Ito yung magiging right-hand side natin. And essentially, we're looking for the solution ax equals b, where x would be an n by 1 matrix, right? Or it's a vector consisting of n complex matrix. And we said that the singular value decomposition of A, of the matrix A, is basically a type of factorization of the matrix A. We try to write the matrix A as a product of nice matrices. So you have a matrix A. Ang goal natin, masulat siya as U sigma V conjugate transpose. So I'm using conjugate transpose because I'm assuming that our matrix A has complex entries, right? So recall that if you have a matrix A, na ang laman niya ay Aij, pag kinuha mo yung A conjugate transpose, ito ay itatranspose mo muna yung matrix, so magpapalit yung row at saka column number. Tapos dahil naka-complex conjugate siya, kukunin mo yung complex conjugate ng bawat entry. So you get the transpose of your matrix A and then conjugate the entries. If A is real, so kung puro real lang yung entries ni M, ni matrix A, then its conjugate transpose is just equal to its transpose. Right? So yun yung idea rito. So in MATLAB, kapag meron ka matrix A, tapos nilagyan mo siya na, kay MATLAB, A apostrophe, ang default ay ito ay complex conjugate transpose. Complex transpose. So kung merong complex entry si matrix A prime kay MATLAB, conjugate transpose yung ibibigay niya. Pero kung gusto mo i-transpose lang ng matrix kahit meron siyang complex entries, ang kailangan mong i-type ay A dot transpose. Ito naman yung usual transpose natin. Kapag kasi A ay complex, because if A consists purely of real entries, then it doesn't matter because A transpose is equal to A conjugate transpose. Okay? So, but that's the basics. So I hope you remember what the conjugate transpose V star means, all right? So ito ay gusto nating i-factor yung matrix A. Isulat siya sa product of three matrices, U, sigma, and V conjugate. Okay? Now, what are the requirements? Kasi hindi unique ang factorization ng matrices. Hindi siya katulad ng prime factorization na unique. So mas ano siya, parang random or arbitrary factorization. Pag hindi sinabing prime factorization, then posible tayong iba-iba ng factorization for a number. So for instance, 6 can be written as 6 times 1 or it can be written as 3 times 2. So you can consider those as two factorizations. Sa matrices, ganun din. Kaya lang mas maraming posibleng factorization sa isang matrix. Now, the SVD is a very nice factorization in such a way that each of the components has interesting properties. So for instance, the matrix U, which is basically, we want the matrix U to be an M by M. So it's a square matrix. So sulat ko na lang yung isang subscript. Pagka M sub M, understood natin to na M by M. It's a square matrix consisting of complex entries. Tapos si V ay N by N naman, consisting of complex entries din. Okay. And yes, and the nice thing about U and V are they are unitary. Ito yung i-require natin na properties to get a unique decomposition or to get a class of decomposition. So dapat si U at saka si V ay dalawang matrices, si U ay M by M, si V ay N by N, tapos sila ay unitary. When we say unitary matrices, ibig sabihin lang nun, ang kanilang inverse ay yung kanilang conjugate transpose. So meaning U inverse, wala tayong problema sa inversion kasi ang U inverse lamang ay U conjugate transpose, and the same thing for V. V inverse is V conjugate transpose. So yan yung requirement natin para doon sa U and V. Moreover, ang requirement naman natin kay sigma ay dapat siya ay diagonal. It's a diagonal matrix. Though it's a little bit odd or different because kapag meron tayong diagonal matrix, ang kino-consider lang natin dati mga square diagonal matrices. So, but you can generalize it to rectangular matrices. So that means sigma is an M by N complex matrix. So element siya ng set na yan. Kapag medyo mahaba yung sulat, yung mirror image sigma, pwede siyang basahin as sigma is an element of this guy. Ayoko kasing isulat dito yung is an element of, kasi dito ko isusulat ko yung itsura ni sigma. Right? So si sigma ay diagonal. So ibig sabihin, magkakaroon lang siya posible ng non-zero entries kapag kayong row number at saka column number are equal. Alright? So ang magiging itsura niya, sigma 1 or little sigma 1, sigma 2, until sigma, let's say sigma r. Okay? Tapos, 0 na siya dyan, 0 na siya dyan. Tapos, meron ding bunch of zeros dito sa baba. Okay? So again, a diagonal matrix is a matrix that only has, that will possibly, ano ba sabihin? Alright. A diagonal matrix is a matrix na 0 yung entry niya whenever the row number is not equal to the column number. So ibig sabihin, we can write sigma in a block form. So ibig sabihin, yung unang block, which is basically this, tawagin natin siyang what? Tawagin ko siyang S, tapos zero matrix tong sa baba. So it can be thought of as a rectangular diagonal matrix. So ito yung R by R rectangular matrix sitting on top of what? What is its size? A zero matrix of the appropriate size para maging M by N yung matrix na sigma. Okay? So we'll see an example of this later, pero pwede nyo isipin, diagonal matrix S nakaupo sa ibabaw ng isang zero matrix. Or isang matrix that only has zeros in it, and the size of that zero matrix is dependent on R para yung para yung matrix sigma ay maging M by N yung size. Okay? So that's what we want for the SVD, for the singular value decomposition. So we want to write the matrix A as a product of a unitary matrix U times a diagonal matrix sigma times another unitary matrix V conjugate transpose. Okay? And with all of these properties, double check nga natin kung tama. So ito ay M by N. This guy is M by M. This is M by N. This is N by N. So that means the product is M by N as expected. Okay, I think we have the right sizes here. Okay? So yan yung gusto nating mangyari. And then dun sa video, I hope you remember na maganda pala yung singular value decomposition. Kasi one property of this decomposition is that the sigmas or the entries of the diagonal matrix sigma, ang tawag natin sa kanila ay singular values. So the sigma sub j's are the singular values. And the convention tells us that they should be in decreasing order. So that means sigma 1 is larger than or equal to sigma 2, greater than or equal to sigma 3, and so on. So yung mga singular values ay naka-arrange in decreasing order. And the singular values tells us the weight of each of the columns of U and V. Ang tawag natin sa mga columns ni matrix U at saka ni matrix V ay mga singular vectors. So essentially, you can think of it as writing the matrix A as a linear combination of the product of the singular vectors. Actually, if you are patient enough and to write the expansion, so pwede mong isulat si A, si matrix, okay, in this form, si matrix U, sulat natin na U1, U2, U3 hanggang UM. Okay? Siya dapat ay M by M. So yung U sub I, siya yung mga columns ni matrix U. So columns yan. Tapos you have sigma here. Papayin ko na lang si sigma from here. And then we'll have V1, V2 until Vn column vector, pero iko-conjugate transpose ko yan. Now, if you're patient enough and carry out this multiplication, you will know or you will see that the matrix A is now written as sigma 1 U1 V1 conjugate transpose, the sigma 2 U2 V2 conjugate transpose, plus until the last one. So this would be sigma R kung ilan yung non-zero o yung, kung ilan yung kung ano yung size ng diagonal matrix S dito, you'll have V sub V sub R, then V sub R star. Okay. Now I don't the other remaining terms kasi nga si R I actually R is the minimum, or usually R is the minimum between M and N. So ibig sabihin yung mga sobra na kay R, hindi sila nagko-contribute dun sa decomposition ni A. Because one property of these matrices ay sila ay mga orthonormal bases. So ibig sabihin lahat ng mga m-dimensional vectors ay kaya kong isulat as a linear combination ng mga u sub i's, at lahat din ng mga n-dimensional vectors ay kaya kong isulat as a linear combination of the v sub i's. And basically, you can think of the singular values to be the weights assigned to each of the basis elements. So ibig sabihin, kung si A ay i-expand ko in terms of these products, pwede ko pala siyang isulat as a linear combination of the column vectors of U times the conjugate transpose of the column vectors of R. So ibig sabihin, pwede kong tingnan as si A ay sigma 1 piece of this product, then sigma 2 piece siya nito, sigma R piece siya nito. So basically, yung sigmas, yung mga singular values natin, yung nagsasabi na gaano kabigat or gaano kalaki yung influence ng mga vectors na to o yung dot product ng mga singular vectors in the representation of A. Remember, lambda 1 and the lambda R are in decreasing order. So ibig sabihin, kung nasa lambda 100 ka na, napakaliit na ni lambda 100 possibly compared to lambda 1. So ibig sabihin, yung pang 100 na column ni A at yung pang 100 na column ni V ay konti na lang yung contribution niya kay capital A. If lambda R is small enough, then you can just ignore it. Yun yung ginagawa natin. Kumukuha tayo ng isang low rank approximation para kay A. Kasi sabihin natin, marami namang columns ang hindi na nagmamatter. Kasi dun sa expansion, napakaliit na nung weight na singular value attached to them, meaning the weight assigned to that product is very small, so we can just ignore it. So parang sa Taylor series expansion lang. Habang lumiliit si H, pwede nyo i-truncate yung mga nasa dulo ng expansion kasi super liit na nila. Dito ay ganun din. Kaya lang matrix yung ating tinitingnan. Victor, sigma yung ginagamit kong letter. So this is how I write sigma. Pag lambda, ang sulat ko ng lambda ay ganito. Medyo kailangan clear tayo. Kasi yung lambda, usually ito yung ginagamit para sa eigenvalues. And probably that's what you're thinking of, eigenvalues. And sigma, usually ito yung para sa singular values. Meron kasing tinatawag rin na eigenvalue decomposition. You're writing A as the product of X, then sigma X conjugate transpose, where X is unitary. Tapos si sigma, diagonal din siya, diagonal matrix din siya, pero ang laman niya ay mga eigenvalues. Pero tayo, tinitingnan natin ay mga singular values yung tinitingnan natin as sigma. So be careful. So pag nagbabasa kayo ng literature, hindi porket nakakita kayo ng ganito yung itsura, siya na yung singular value decomposition. Double check kung ano yung tawag niya dun sa mga diagonal entries. Kasi if they're using lambda, hindi lang sila nag-change of notation. So malamang ang pinag-uusapan nila ay eigenvalues at hindi singular values. Now there are several advantages, and it's a nice thing that Victor raised that issue up. There are some advantages of the singular value decomposition over eigenvalue decomposition. And it's a nice segue for me to note the following facts. All right? Hold on. Meron akong kodigo para sa mga facts. So, theorem. Or theorems. So, the following are known. Every matrix A, even if it's rectangular, or complex value has an SVD. So, laging, kapag ka meron kang isang matrix A, guaranteed lagi na pwede mo siyang may susulat na U sigma V conjugate transpose. Hindi siya katulad ng eigenvalue decomposition. Hindi lahat ng matrices ay may eigenvalue decomposition. Because eigenvalues can only be computed for square matrices, right? So kapag ka rectangular na yung matrix mo, hindi mo na siya mahahanapan ng eigenvalue decomposition. Okay. And another thing is that the sigma j's, even though the matrix factorization in general is not unique, but the sigma sub j's are uniquely determined. Kasi posibleng magbago yung U at saka yung V transpose. You can find some other decompositions or singular value decompositions for your matrix A, pero it will just be up to a scaling of the singular vectors. The lambda sub j's are always uniquely determined, probably up to some scaling factors, but the thing is, pag lumaki naman yung isang singular value, lalaki rin yung iba by a scalar factor, so it doesn't really matter. So you can think of them as being uniquely determined. And then if A is square, then the sigma sub j's are distinct. Oh, by the way, yung mga sigma sub j's, yung iba sa kanila pwede rin pala mag-zeros. So wala nagpe-prevent na mag-zero yung mga singular values. Some of them might not be zero, meaning most of them will contribute to the expansion of A. Pero kapag ka maraming zero, so kapag ka sparse yung matrix sigma nyo, pero by definition pala yung sigma is sparse na. So kung marami kang sigma, kung marami kang non-zero singular values, then ibig sabihin lahat halos ng columns at saka so columns ni U at saka ni V ano ko contribute dun sa expansion niya. So are distinct, and then the singular vectors when I say singular vectors, ito yung mga column ni U at saka ni V are uniquely determined up to some complex sign. So when we say complex signs, ang real signs lang natin plus or minus 1. Pero sa complex numbers, posibleng meron kang ibang tinatawag na, meron kang scaling constant. Pag sinabi natin complex signs, ito ay isang complex number Z with its absolute value or its modulus equal to 1. So ibig sabihin si negative I ay pwede natin gawing complex sign. Negative I, positive I, 1, at saka negative 1, and some of those na merong real at saka imaginary part ng L2 norm ay 1. Pero don't worry about those technical details. I just want you to get an idea. Why are we using singular value decomposition? Kasi nga maganda rito, lahat ng matrices ay may singular value decomposition. The sigma j's are uniquely determined, even though hindi unique yung singular value decomposition, nakita nga natin dun sa third bullet, ay pwede mong i-scale by some complex signs yung mga singular vectors. Okay? So how will the singular value decomposition help us in solving inverse problems? Essentially, the idea is this. So let's assume we're solving AX equals B. And we have said that the matrix, all matrices have singular value decomposition. So if it's not if A is not huge a matrix, pwede mong ipa-compute with ease yung singular value decomposition niya. And I guess it has number of operations comparable to the inversion procedure. Okay? So kung si A ay may singular value decomposition, palitan natin si A dito sa ating equation by its singular value decomposition. So I can write it as U sigma V conjugate transpose times x equals b. And then I can multiply both sides by the inverse of the entire thing to get x. This will give us x equals u sigma v conjugate transpose inverse equal kay b. Sorry, times b ay equal kay x. Okay? Tapos, gagamitin ko yung properties ng inverse ng isang matrix or inverse ng product ng matrices. So if you have taken linear algebra, Math 105, or even Math 111, so kapag ka meron kang product, tapos ini-invert mo, tapos hindi commutative yung product, kailangan mo lang i-reverse yung order at lagyan bawat isa ng inverse. So ang U sigma V conjugate transpose inverse ay V conjugate transpose inverse times sigma inverse times U inverse times B. But the nice thing here is that we know that U and V are unitary, meaning their inverses are simply their conjugate transpose. So, ibig sabihin, ito ay equal lang sa V conjugate transpose, conjugate transpose. Si sigma ay diagonal. So, ang itsura lamang ng inverse ng isang diagonal matrix, you can check. But the inverse or the pseudo-inverse, depende kung nag-exist yung inverse or hindi. Pero in general, the pseudo-inverse of a diagonal matrix is another diagonal matrix consisting of the reciprocals no kanyang diagonal entries. Oh, this will work if all of the if all the diagonal entries are non-zero. And let's just assume that for simplicity here, if that's not the case, then you need to get the pseudo-inverse of sigma inverse. So, medyo may bubu ako rito in notation. So, dapat ito ay pseudo-inverse. Kasi nga, hindi ko pa sure kung nag-exist yung inverse ni sigma. So, hindi pa siya mag-exist kasi posibleng si sigma ay rectangular. Right? So, ang naman niya ay 1 over sigma 1, 1 over sigma 2, 1 over sigma 3, hanggang 1 over sigma r, tapos 0 na siya everywhere. So, ito yung property ng pagkuha ng inverse ng isang diagonal matrix na non-zero yung diagonal entries. Okay. And then U inverse is simply the conjugate transpose of U times B. So, ito yung solution natin. Oh, actually, I can simplify it further kasi ang V conjugate transpose is simply V. Tapos, meron tayong 1 over sigma 2, 1 over sigma 3, hanggang 1 over sigma r, assuming all of them are non-zero, zero na yung ibang entries, times U transpose. So that's going to be our solution. Okay. Now, the problem here is this is akin to a naive reconstruction because we're simply taking the inverse of the matrix A. And we have seen that if we have an inverse problem and we got the matrix A as a representation of the model or the propagator or the operatorial form of the forward problem, I see A inverse or yung problem na to ay ill-posed. Meaning even if you can compute A inverse in an efficient and accurate manner, posibleng hindi mag-work yung or hindi maganda yung reconstruction mo kung tainted by noise or by measurement errors yung right-hand side B. Okay. So again, if you know B is a perfect data, right? Walang error dun sa measurement. Or it's a classroom problem, wala ka namang measure, given lang talaga yung exactong B, then this is a straightforward solution. Kaya lang pag in-implement mo na to sa machine, hindi na siya ganun ka-efficient kasi at least yung diretsong inversion. Kasi ito ay tinatruncate na, pinuputol yung number of decimal digits kay B. Kung meron ka dyan mga irrational numbers, ika-cut siya to a certain number of significant digits para mag-cache siya sa memory ng inyong computer. Tapos doon magagana yung arithmetic of your CPU or of the programming language that you're using. So maraming mga involved. Pero kung everything is perfect, then this is a good solution. Because once you get the SVD, wala ka na kailangang inversion. Pagko-conjugate transpose na lamang yung kailangan. Kaya lang, ang problema natin ay konteksto tayo ng inverse problem, yung pinag-aaralan natin. So our B is not a perfect data. So this B is tainted by measurement noise. And as much as possible, we want to eliminate the effect of measurement noise in our solution. Okay? So essentially, what we're trying to do is instead solve AX equals B plus some error vector epsilon or noise vector epsilon. Okay? So ito yung gusto nating isolve. And then let's call the solution X tilde. Diba si X tilde yung ating solution from the noisy measurements. Okay. Now we can do the same thing. Represent A in terms of its singular value decomposition. Take the inverse of that decomposition and apply it to both sides of the equation. So essentially, we'll have V sigma pseudo inverse times U conjugate times quantity B plus epsilon. Ito yung makukuha nating solution. Right? And then I'll use the distributive property of matrix multiplication over vector addition. So this would be V epsilon pseudo inverse sigma B plus the same guy, but this time multiplied to the error vector epsilon. So yan yung makukuha nating solution from noisy data. Now, when we compare the actual solution we got, let's call the actual solution X star. So yung actual solution ay ito. I-compare natin siya dun sa solution mula sa noisy data. Basically, I'm computing X star, the true solution, or the reconstruction from perfect data minus the reconstruction from noisy data or your tainted data. This will just be equal to V pseudo inverse ni sigma U star B. So essentially, this is the exact representation for X star. Then galing dito, right? Pinperform ko lang yung mga inversions. So I got it there. Minus this quantity. Okay. Pag kinuha natin yung discrepancy between the true solution and the solution from the noisy data, we'll see that, oops, this guy will be canceled by that guy. So we'll be left with this one. So negative V sigma plus U star epsilon. Okay. So titingnan natin gaano kalaki to. Kasi gusto natin makita ano yung epekto ng noise dun sa ating solution. So basically, instead of solving lang pala yung residual vector or discrepancy vector between the true solution and the noisy solution, I'll take, say, the L2 norm of both sides. Para alam natin ano yung size nung discrepancy sa pagitan ng dalawang solutions na nakuha natin, true solution and noisy solution. Okay. Now, itong negative sign na to, mawawala yan kasi nasa loob siya ng norm. So this would be V sigma plus star sigma L2 norm. All right. And then the Cauchy-Schwarz inequality tells us that if you're taking the norm of a product, it is less than or equal to the product of the individual norms. So it's going to be norm ni V times norm ni sigma times norm ni U times norm ni epsilon. Okay. Norm of epsilon is basically how big the noise is, right? So ito yung ginagawa natin na ang relative noise ay 1%, so epsilon would be 0.01 times the size of the vector, the right-hand side vector, the true right-hand side vector, right? Pero paano pa natin ito masisimplify? Isang property, hindi ko alam kung nabanggit ko kanina, kaya dahil pala nag-code talaga ako. Hirap na i-live, ano? Pero essentially, isang property nung U at saka ni V, aside from them being unitary, orthogonal. Hindi lang orthogonal yung mga columns nila, pero orthonormal din. When you say orthonormal ang isang matrix, ibig sabihin ng L2 norm niya ay equal to K1. Essentially, the norm of V is 1. The norm of U conjugate is also 1. So this guy is just the norm of the pseudo inverse of sigma times the norm of epsilon. Right? So ito yung upper bound natin para dun sa discrepancy between the true and the noisy solution. But what is the norm of sigma star? Well, this is of sigma pseudo inverse. Well, this is something that I should have mentioned earlier. Nakalimutan ko siyang bagitin part of the theorems, or if you can recall from previous discussion when we talk about norms, that the L2 norm of a matrix is basically its largest singular value. Okay, so it means that kung si matrix A ang kanyang L2 norm ay yung highest eigenvalue niya. Largest singular value niya. Yung sinabi natin kanina, no? Arranged in decreasing order, yung mga singular values of the largest singular value, sigma sub 1. The first entry in the diagonal matrix sigma. Ito yung pinakamalaking value. That's the largest singular value. And the way we define the L2 norm of a matrix, ang L2 norm ng isang matrix ay ang kanyang pinakamalaking singular value. Right? The L2 norm of the matrix A is sigma sub 1. Okay. And this is basically, pwede ko itong isulat na V. Actually, it can be shown. Hindi ko na ipapakita yung solution, but this is the same as the singular value or the L2 norm of the matrix sigma. And also here, I'll give it without proof that what do you think would be the L2 norm of the pseudo inverse of sigma? Sigma. Yeah, I can flash how sigma looks like. Ito na pala napakita. Ito si sigma. Ito si sigma pseudo inverse. What do you think is the L2 norm of sigma pseudo inverse? Kasi ito yung kailangan ko dun sa ito yung kailangan ko dun sa discrepancy. So, what's the L2 norm of this guy? Kapag meron kang diagonal matrix, you can think of its L2 norm to be the largest diagonal entry. Yun lang yung L2 norm ng isang diagonal matrix. So we know that the sigmas, sigma 1 until sigma r, are arranged in decreasing order, so that the norm of sigma, the L2 norm of sigma, is equal to 1. Question: what is the norm of sigma pseudo inverse? Knowing that sigma pseudo inverse looks like this. Ano to? Ito yung gusto kong mahanap. Ano yung norm ng sigma pseudo inverse? 1 over sigma r. Yes, you will be right, Neo. Thank you, Neo. Yes, 1 over sigma r. Kasi usapan pinakamalaking diagonal entry. Remember that the eigenvalues are arranged in decreasing order. So sigma 1 is the largest, sigma 2 is the second largest, sigma 3 is the third largest, and sigma r is the least singular value. Then you reciprocate them, all right? So sila yung bumuo ng diagonal entries ni sigma pseudo inverse. So that means the largest among these guys will be 1 over sigma inverse. Okay? So that means if we go back here, so yung discrepancy or yung norm ng discrepancy x star minus x tilde in the L2 sense ay bounded above by the L2 norm of sigma pseudo inverse, which, as Neo stated, it's 1 over sigma r times the norm of the L2 norm of the error vector. Okay? And when will this be? But again, we note again here where sigma r is the least eigenvector, or sorry, not eigenvector, it's the least singular value of A, right? And remember, our goal is to make x tilde as close as possible to x star. Tama? Kasi gusto natin na yung maliit na noise, dapat maliit lang yung contribute niya. Kaya lang, kahit maliit yung noise mo, meron ka namang scaling factor, which is 1 over sigma sub r. So, what can I do in order to minimize the discrepancy? Again, wala tayong control sa noise vector kasi yung noise vector ay it naturally occurs, right? Or in measurement or in data measurement, siya yung accuracy or precision ng ating measuring device. So how can I make this smaller, knowing this inequality here? How can I force the discrepancy to be smaller? Actually, medyo mahirap pala yung tanong ko kasi wala rin tayong control kay sigma sub r, tama? Kasi si sigma sub r, siya yung pinakamaliit na singular value ng ating matrix A. So kung masyadong maliit yung kanyang smallest singular value, ibig sabihin yung 1 over sigma r ay lalaki. So ma-amplify by 1 over sigma r factor yung size ng ating noise. Wow, 1% lang yung noise mo. So ito, halimbawa, 0.01 lang. Kung 1% yung noise mo, pero ito ay 10,000, ang laki ng discrepancy. Okay? So the idea is, since this is hardcore, this is from measurement, so we cannot do anything about it. Maybe we can see if we can play around with this. Of course, we cannot change the singular values for a matrix A. Wala tayong kakayahan na paliitin yung mga hindi natin nababago yung mga singular values. But we can replace A by a low rank approximation using the singular value decomposition by ignoring some of the least eigen, sorry, not eigen. Why am I going eigen ng eigen? When we ignore the small singular values. Because remember, sabi natin kanina, si matrix A ay pwede mong isulat na sigma 1, U1, V1, conjugate transpose. So basically, the dot products of the singular vectors scaled by sigma sub 1. So si sigma sub 1, itong first term na to, ito yung pinaka-significant building factor. Ito yung may pinakamalaking ambag. Itong product na to, yung product na yan. So yung first singular vector, sila yung may pinakamalaking ambag para mabuo si A. Kasi nga yung mga UI-VI conjugate transpose, sila yung mga building blocks ni A. Pinagsasum lang natin sila to get A. Ang weights nila ay yung mga sigmas, yung mga singular values. So this is the most dominant term. Followed by sigma sub 2, U1 U2 V2 conjugate transpose, sigma 3, U3 V3 conjugate transpose, all the way up to supposedly pupuntahan natin lahat ng column at saka lahat ng rows ni A. Kaya lang posible mag-zero yung ibang singular values. So pwedeng ito ay hanggang sigma r minus 1, ur minus 1 star, walang star to, br minus 1 star, the sigma r, ur, br, sigma star. Ayan yung eksaktong expression para kay capital A. But what if, since naka-decreasing order yung sigma, sabi nga nung sa video, nakalimutan ko naman yung author, he had a very nice way of putting it. Those in the tail end of the summation doesn't contribute significant amount to the building of A. If you want to fine-tune A, if you want to get the exact value of A, then go ahead. Continue or use all of the singular values and all of the singular vectors. However, if you want to get a low rank approximation, A, you can ignore the singular vectors that are coupled with the small singular values. So ibig sabihin, pwede ko itong putulan up to some point. So pwede ko itong si A, pwedeng ma-approximate by sigma 1, U1, V1, conjugate transpose, the sigma 2, U2, V2 conjugate transpose, all the way up to sigma sub K, V sub K, U sub K, V sub K conjugate transpose, where K is smaller than R. Kaya siya naging approximation na lamang. Kasi tinanggal ko, binawasan ko yung mga contributions or tinanggal ko totally yung mga contributions na kakaunti lang naman yung ambag. Yung mga terms na kakaunti yung ambag dun sa construction ni A, tinanggal ko na sila. Kasi nga may epekto. Kapag kinip ko si sigma sub R na napakaliit, yung noise pala ma-amplify by sigma sub R. Of course, now we are sacrificing accuracy. Because what I'll do, if I'll call this A sub K, so to be the approximation to A using only the first case singular values, then what I will solve is A sub K X equals B plus epsilon. Ito yung isosolve ko instead of AX equals B plus epsilon. So you see now that I am sacrificing some of the accuracy. Kasi eksaktong system may ito. Pero sabihin ko, ayoko mag-compute ng maraming singular values. So ibig sabihin, puputulin ko si A o yung expansion ni A to the first K term. So I'm sort of shortcutting how A is written or how A is expanding by lessening the number of terms, ignoring those with smaller singular values. So dito pa lang, bababa na yung accuracy natin. So kung yung makukuha kong solution X sub, tawagin natin X sub T, para ito yung solution X mula sa singular value decomposition, ito ay equals sa A sub K inverse times B plus epsilon. And of course, you can write A sub K inverse in terms of its singular value decomposition. Now, this A sub K inverse will look like V sub K sigma sub K and U conjugate transpose K. Pangit pala ng notation na K kasi nagbumukha siyang subscript, ano? So, lagyan ko na lang ng hat. So, nung tinrangcate ko na siya, lalagyan ko na lang siya ng hat. Huwag pa lang sub K. Basta ang understanding natin ay si A hat, siya yung truncated version ni A. So parang kumbaga sa functions, meron kang Taylor series expansion, tapos kinalimutan mo yung karamihan ng mga terms na nasa dulo kasi you justify it by saying na konti na lang yung contributions nila. Ganun din dito sa matrix decomposition. Since some of the sigma sub k's of the sigma sub j's are small enough, then I can just truncate it to the first k singular values because they will after all dominate the building of the matrix A. And I'll call the matrix obtained in the truncated expansion of A as my A hat. So, A ang makuha nating solution, or dito ay si A hat, ay equal kay V hat, epsilon hat, U conjugate transpose hat. And here, epsilon hat will be still a diagonal matrix, but this time it will consist of an upper building block, which is a smaller diagonal square matrix. Nagkakaroon ka lang ng sigma 1, sigma 2 hanggang kay sigma k. So medyo papayat yung matrix mo, pero medyo tatangkad din naman siya. Kasi magdadagdag ka ng zero matrix dun sa baba niya. So essentially, kaya siya tinawag na truncated singular value decomposition. Kasi kinukuha lang natin yung ilan dun sa mga singular values na involved dun sa expansion. And then now, if you solve for x star, solve na natin bagay natin na rin tong x hat para consistent yung notations natin. So, si x hat ay equal dito. Alright. So pag kinuha natin yung true solution minus x hat, of course, nag-sacrifice na tayo dyan. Kasi medyo malaki na yung naging error. Pero ang kagandahan dito ay mas mapapaliit natin yung epekto ng noise. Kasi if we will look at this, mangyayari sa atin ay magkakaroon tayo ng isang term. Of course, there would be some error. Tawagin mo siyang curly E due to the truncation of A from the singular value decomposition. Pero ang gusto kasi dito tingnan, understood ko na bababa talaga yung accuracy ng konti. Kasi yung expansion ni A, pinutol mo lang to some point. So understood. Iba na yung system mong sinusolve, which if K is large enough would be a good approximation to K. But I don't want K to be I don't want K to be too large. That is as if I'm using the full singular value decomposition kasi nga gusto kong mabawasan yung epekto ng noise. So yung epekto ng noise dito ay actually magiging minus 1 over sigma K times the norm of epsilon. Okay. Kasi nga, instead na sigma R, puputulin ko na yung singular value decomposition hanggang sa unang K na singular values lamang. So, ang pinakamalaki na nga yung fraction doon sa sigma hat. Doon sa sigma hat ay 1 over sigma K. And 1 over sigma K is definitely smaller than 1 over sigma R. Right? So kaya mas nami-mitigate natin yung epekto ng noise kapag gumamit tayo ng singular value decomposition, ng truncated singular value decomposition. But there's still a question. Parang yung Morozov Tikhonov lang last time. So paano kung mapipili si K? Kasi sabi mo magta-truncate lang ako. Kapag malaki si K, marami akong singular values na kini-consider, malaki yung epekto ng noise. Pero mas malapit yung sinusolve ko na system dun sa given system. Pero kapag masyadong maliit si K, masyado nang liliit yung epekto ng noise, pero lalaki naman yung error due to the estimation of A by A hat. So, nag-sacrifice ka naman ng accuracy. So again, you need to find a perfect balance by looking at the nice value for K. There are fancy ways on how to compute the best K, pero mas madali pa rin lagi yung ad hoc. Alright? Randomly pumili ka na lang muna ng singular value ng number ni K, tapos mamili ka na lang later. Parang yung ginawa natin sa alpha. Okay? Now, I uploaded a MATLAB code that sort of implements the singular value or the truncated singular value decomposition in Canvas, and then there's just a module under truncated singular value decomposition. But before I present the code, meron ba kayong mga tanong so far about this theoretical discussion that we had? Questions? Does this make sense? I hope it does. Okay. So, lipat ako sa MATLAB. Tapos yung SVD, the code that I wrote is called PSVD reconstruct.m. Okay? And I wrote this as an external function para pwede nyo siyang ilagay as a building block ng isang mas malaking program. Right? So I'll just run you through the contents of the program. Okay? So dinefine ko siya as an external function para pwede nyo siyang tawag-tawagin as long as the file tsvd reconstruct.m is in the same folder as your bigger code or your main program. So dapat parehas sila kung saan sila nakasave. Now, ang output ng function na to, when you call it in another program, ang output niya yung XR alpha, which is, in my derivation kanina, ito yung X hat. Ito yung solution after keeping the first R sub alpha singular values. The R sub alpha, makita nyo mamaya sa inputs, siya yung kung ilang singular values yung gagamitin nyo o yung ititira nyo. Okay. Now, in order to call this in your program, tatype nyo lang sa main program tsvd reconstruct, tapos magko-compute siya. You can save the variable into whatever name you want. Maybe I can demo that later kung di pa rin kayo familiar sa external functions. Tapos, dapat merong 4 na inputs yung TSVD reconstruct. Una, ipapasa mo sa kanya yung matrix A, yung iyong system, yung coefficient matrix. Papasa mo rin sa kanya yung right-hand side B. And the right-hand side B should already include the noise. So pwede mo nang i-simulate. Pag pinasa mo siya kay TSVD reconstruct, dapat factored in na kung may noise man yung measurement. So nandun na siya kay matrix, kay vector B. Si R sub alpha, siya yung ilang singular values yung pwede mong gamitin. Now, the maximum value, or R sub alpha, the highest possible value of R sub alpha is the minimum between the row number, the number of rows and the number of columns. So kung meron kang 100 by 50 matrix, meron ka lang doon at most 50 non-zero singular values. Kung meron kang 64 by 64 matrix, so meron kang maximum 64 non-zero singular values. So it's always the smaller between the number of columns and the number of rows. Tapos itong graph SVD, this is either 0 or 1. Mag-input kayo dapat ng 1 kung gusto nyo i-plot yung singular values para makita nyo gaano kalaki yung mga singular values. Kasi pag nakita mo yung singular values ni A, tapos super liliit ng mga nasa dulo, then that tells you kailangan mo mag-truncate ng mas marami. Kailangan mas maliit yung R sub alpha mo kung sobrang liliit yung mga singular values sa dulo. And sometimes if you want to find that optimal R sub alpha, then you should have a look at how big are the singular values. Okay. Tapos ito yung sinasabi rin dun sa video, one-liner lamang yung pagko-compute ng singular value decomposition ng isang matrix kay MATLAB. So ang command para doon, ito ay built-in kay MATLAB, SVD. So just call SVD of your matrix. Magbibigay siya sa iyo ng 3 vectors if you write it this way. Ibibigay niya yung unitary matrix U, yung diagonal matrix sigma, at saka yung unitary matrix V. Okay? Tapos yung singular values ni matrix A ay yung diagonal entries ni S. Si S yung sigma rito. So pag kinuha mo yung mga diagonal entries ni S, and you can do so by calling diag of S. Yung diag of S, i-harvest niya lang yung mga nasa diagonals ni S. I-save niya lang yon sa matrix ng tawag ay sa vector ng tawag ay S-values. Okay. Ginawa ko to para lang makita ano yung itsura ng mga singular values. Para malaman magka-idea ko ilan yung dapat kong i-truncate. Now, i-graph sa line 17 to 23 yung mga singular values para makita natin yung magnitude nila. Okay? But only if naka-1 yung graph SVD na input, which is the 4th input na dapat ipasa nyo kay TSVD reconstruct. Kasi minsan, kapag ka nasa isa kang loob ng for loop, ayaw mo namang mag-graph ng mga SVD ng paulit-ulit, so you can turn it off. Right? I-zero mo lang to, or any number aside from 1 will do for graph SVD para hindi niya i-plot yung mga singular values ng paulit-ulit kung nasa loob ka ng for loop. Okay. And then lines 25 to 30, kino-compute niya lang yung X sub alpha. Ito yung ating V star sigma pseudo inverse times U conjugate transpose times B. Yun yung XR sub alpha. Ito yung solution, pero gamit ko na yung truncated singular value decomposition. Kasi dito sa line 26, line 27, pinaliit ko na ngayon si sigma. Si sigma na lamang, which is supposedly, or S plus, supposedly to be the sigma pseudo inverse, consisting, which is a diagonal matrix consisting of the reciprocal of all the singular values. Pero sabi ko nga, tinatruncate natin dito. Gumagamit lang tayo ng first R sub alpha singular value. So, kukunin ko yung S plus, sigma plus. Actually, in our derivation kanina, ito yung tinawag ko na sigma hat. plus. Ito yung pseudo-inverse ng sigma hat. So, i-consider ko lang yung first hanggang dun sa R alpha, the singular value. So, the first R sub alpha singular values. Tapos, yun yung gagamitin ko para makuha yung reconstruction natin using the singular value decomposition. Okay? So, yun lang. Yun yung code, di ba? Medyo simple lang naman yung code. Kaya nga nung sinusulat ko to, sabi ko, kailangan ko siguro ng 2 hours para isulat yung code. Pero parang 15 minutes pa lang tapos ko na itong isulat. Kasi simple lang pala siya, right? So, yeah, that's the code. Probably I could demo how it is used. Siguro ang kagandahan nito, pwede ko siyang gawin sa command window kasi external command siya. Just make sure you are on the same folder. So makita mo naman dito sa kaliwa kung ano yung current folder mo. Or if you're lost, hindi mo na matrack, pwede kang mag-right click dito sa tab. Dun sa may pangalan na TSVD Reconstruct, right click it. Pwede kang pumunta dun sa folder na nagko-contain nung TSVD Reconstruction. Okay, so ano man ito? Change current folder to this guy. Pupunta ka na dun sa folder kung nasaan yung TSVD Reconstruct.m. And naka-gray to kasi nandun na ako. So, hindi niya ako ililipat. So, remember the PSF problem, the convolution problem that we have? Luckily, I already saved the data. So, from my folder, I'll just click condata.mat, this current folder. Kasi nga matagal, di ba, mag-compute ng convolution. So, niload ko lang yung mga data. Tapos, tinama ko na yung dimensions. So, makikita nyo rito si data X saka si data Y ay parehas ng 64 by 1. So, column vectors na sila. Yung error vector ay 64 by 1 na rin. So, hindi ko na kailangan yung transposition na ginagawa ko before. Kanina, inedit ko itong data na to. Alright. And then now, I can just, so I have the matrix A here saved. I have the right-hand side B saved, which is data Y. And then what else? Yeah, so nasa akin na lahat ng ingredients para i-call si TSVD Reconstruct. But before that, let's just recall how does the solution or how do the solutions look like na nanggaling dun sa exact data at saka yung nanggaling dun sa noisy data. So I think okay. I think ito yung kailangan kong i-run, line 67 to 75, yung PSF.m para pa-plot yung solution from perfect data. Okay, so ito yung nakuha natin kung perfect yung right-hand side vector B natin. But again, this doesn't happen in practice, so kailangan nating i-simulate yung noise. So dito, 1% noise yung ginawa ko, tapos ito yung naive reconstruction ko. So if I will not do regularization, this is what I'll get when I have noisy data. Okay. And you see how different it is from the actual F. Ang gusto nating makuha or ma-approximate ay yung kulay green. Pero medyo malayo na pag may 1% noise. Actually, ang laki nga nung epekto. Nakita na natin to before. Ang laki nung epekto ng 1% noise doon sa reconstruction. Now, we can use a truncated singular value decomposition para makita yung solution. Pero ang problema, hindi pa natin alam kung ano yung singular value o ano yung R sub alpha na gagamitin. So when you're playing with it, you can play on the command window or you can open another tab. Tapos dito ang gagawin ko lang, ano nga bang gagawin ko? Magbibigay ako ng, compute ko si F solution or reconstruction for F using TSVD. Tapos ito ay gagawin kong equal kay, i-call ko yung external function na truncate, ano ang title nun? Title nun ay TSVD reconstruct. Tapos parentheses. Tapos i-guide ka naman ni MATLAB, ano nga yung mga inputs dito. So enter a value for A. This is the coefficient matrix that we have. So nasa workspace ko na naman yung 64 by 64 matrix na ginamit natin dun sa convolution problem. Okay, comma, enter a value for B daw. B is the right-hand side data. Alright? Pero right-hand side data dito ay noisy. So data Y, ito yung perfect data, plus lalagyan ko siya ng 1% noise. So yan yung B na ititreat ni TSVD reconstruct. So ipapasa niya itong vector na to to be the second entry kay TSVD reconstruct. So pag nag-run ngayon si MATLAB, alam niya yung data Y plus E, siya yung second entry na nandun sa function, second entry ay B. So pag na-receive ni MATLAB ni TSVD reconstruct yung data Y plus E, alam niya ito yung value ni B na gusto natin paglaruan. Okay. Then the third argument for TSVD reconstruct ay R sub alpha. Ilang singular values yung gusto nating i-keep. Ano yung size ng matrix natin? 64 by 64. So we will have at most 64 singular values that are non-zero. So we pick. Halimbawa, 5 lang yung i-keep natin na singular values. So yung 5 lamang na pinakamalaking singular values yung gagamitin natin dun sa expansion. And then let's see what the results would be. Tapos, do we want to graph the singular values? Yes, 1 yung ilalagay. Okay? And then, i-plot natin kaya yung solution. Okay, copy-paste ko lang yung pagpla-plot dito. Copyhin ko itong galing sa PSF. Kasi gusto kong i-recreate yung plot. Kaya lang ngayon, ang pinagkaiba lang galing sa meron tayong regularization na gagamitin. Gagamit tayo ng truncated singular value decomposition. So, what we'll plot is not fsol and noise kasi ito yung walang regularization na naganap. Papalitan ko ito ng fsol and ESVD. Okay. And then ito ay papalit ko rin dito. Tapos scatter plot based on noisy data, reconstruction of F from noisy data, actual, okay. Palitan ko lang itong title. So gawin natin itong naive reconstruction of F from noisy data. With R sub alpha equals, right? So parang nandun sa title nung graph ko kung ilang singular values yung ginamit ko. So kailangan ko itong enum S2R, yung R sub alpha. I think this should work. So itong pagpa-plot na to ay ipa-plot niya yung solution para ma-compare natin yung solution na nakuha natin from the regularized reconstruction from the actual solution. Tapos i-compare ko to dun sa dalawang figures natin kanina. Right? And you see how convenient finding the solution with the TSVD is. Dun sa TSVD na external program na binigay ko sa inyo, kinol lang siya talaga dito. So you don't have to do it over and over again. Now, if I press F5, sabihin ni MATLAB, i-save ko to. Save ko to ay try TSVD and title. Save. And then it will run. Oh, ano ang problema? R sub alpha. Sorry. Hindi ko pala dineclare yung R sub alpha rito. Diniretso ko siya ditong ilagay yung 5 sa R sub alpha. But you can assign the value of R sub alpha above and then just copy the variable R sub alpha dito para ma-recognize din siya ng legend ko mamaya. So I'll run this again. I'll get this. Wala nang reklamo. So using 5 singular values lamang, ito yung makukuha nating solution. So naive reconstruction from noisy data with R sub alpha equals 5. Medyo malayo. Actually, hindi pala medyo. Napakalayo niya dun sa true solution. Kita niyo to. So, ibig sabihin, kailangan nating mag-keep ng mas marami pang singular values. Hindi lang 5. 64 tayo kanina, di ba? So, we have lots of freedom here. And dahil pinag-graph ko yung singular values, dahil 1 yung nilagay kong last input dun sa TSVD reconstruct, nag-produce si MATLAB ng graph ng singular values. So makita nyo, ginamit lang natin yung 5 pinakamalaki. 1, 2, 3, 4, 5. Ito lang yung ginamit natin. Pero ang dami pang singular values between 10 to the negative 1 and 10 to the 0. So ito, hanggang dito, pwede natin siyang gamitin. Kasi parang 0.1 to 1, medyo malaki pa yung singular value. Malaki pa yung contributions nila compared to the ones here na medyo maliit na. Kasi 10 to the negative 2 na to. So medyo maliit na yung contributions nila. So maybe, just maybe, to get a better approximation to the solution, kasi nga, napaka-stable na nito with respect to noise, pero hindi siya accurate. So ibig sabihin, hindi ko napili yung optimal R sub alpha. So dahil meron tayong 64 na singular values, maybe let's try half, 32. Kalahati ng mga singular values yung gagamitin ko. So I'll set R sub alpha equals 32. I'll hit F5 so that this little code here will run. And here is our result. And you see na medyo kamukha na siya nung nakuha natin kanina na actual solution. Medyo marami na akong figures na bukas. So, hindi ko na makita yung kanina. Okay. So, you can play with it. R sub alpha ay equals, sabihin mo 10 lang. Nagtitipid ka. Para hindi magreklamo si MATLAB ko ay, close all ko muna lahat ng figures. Then I'll run the code again. But now, R sub alpha equals 10. So, I'm going to have just 10 singular values. Kulang pa rin pala yung 10 singular values. Now, it's already time. So, and then, ayoko naman masyado tayong pagmadali today kasi meron pa namang Thursday. So, siguro on Thursday, I'll do the following things. Number one, we'll continue to play with it, and I'll show you one approach, a brute force approach on how to find the best R sub alpha. Ang gagawin natin, ipapatry natin kay MATLAB mula sa isang singular value lang yung ikikip hanggang sa ikikip ko lahat ng singular values. So, MATLAB will run the TSVD reconstruct routine 64 times. Kasi i-record ko ano yung relative error sa bawat isang 64 runs na yon. Tapos pipiliin natin yung may pinakamaliit na relative error. Alright? Para makita natin ano yung best na nakuha natin from the TSVD reconstruction. And then after that, I'll walk you through with homework number 7. So sa Friday ko na, sa Thursday ko na siya ibibigay. Tingnan ko kung kakayanin, kung kailangan pang i-move yung deadline or hindi na. But let's talk about that on Thursday. And then ano pa ba? Yeah, I think that's it. And then we can start talking about the next problem set and the final project. Okay? So I'll stop sharing here. Do you guys have any questions? Questions? So if there are none, so thank you guys for joining me today. And we'll see each other again on Thursday para maglaro pa ng code. So hopefully by then, sana na-download nyo na yung code. Tapos simulan nyo na siyang paglaruan. Tapos i-try and error nyo. Try and error. Inassume ko na may error kagad. I-try nyo na gawin yung dinidescribe ko kanina. Na ipapagawa natin kay MATLAB 64 times yung TSVD. Tapos titingnan natin, pipili tayo alin yung best sa kanila. Okay? So thank you guys. Bye.
Thank you po, sir.
All right.